Hi, and welcome to EngPhys 3004 Lecture 7. This is going to be the next part of Chapter 14, the second of 4 lectures that we're going to do on Chapter 14 in the textbook. And this one is on turbulent flow in pipes, specifically on how to calculate the friction factor and subsequently the head loss for a given section of fully developed turbulent flow. First of all, to recap, last time we calculated the head loss in laminar flow was related to the pressure loss divided by rho g and was calculable via the friction factor, or Darcy friction factor F, multiplied by the length of the pipe, diameter, possibly hydraulic diameter if it's not a circular pipe, velocity average squared, so average flow velocity squared, divided by 2g. So there's a formula that you can calculate. All you need to know is the friction factor, which you could figure out if you knew what the Reynolds number was and the shape of the pipe pretty easily from something like this table. Then you could also calculate the rest of the head loss from that friction factor, because you would know what the average velocity is, pipe diameter, and length of the pipe that you're concerned with. You could calculate head loss per unit length by just dividing both sides by L. All right, for turbulent flow, we're going to use this exact same formula. The only difference is how we calculate the friction factor. So the reason you need to use a different formula to get the friction factor is that the assumptions for laminar flow don't apply to turbulent flow. The velocity profile we derived last time doesn't work anymore, and this is mostly because the inertial effects are so important that the viscosity effects of the walls can't influence the center of the flow nearly to the same extent as they did in laminar flow. There's so much mixing going on in turbulent flow and non-steady streamlines, things changing instantaneously, that the assumptions we made last time don't work, and we have to rely on experimentally determined things to figure out how things are working in turbulent flow. So here is what the velocity profile in fully developed turbulent flow looks like. You can distinguish between a viscous sublayer, a buffer layer, an overlap layer, and what's called the turbulent layer, where you've got all these intense vortices and lots of mixing. The viscous effects are most important the closer you go towards the walls in this viscous sublayer. We, again, still can use this head loss equation in terms of the friction factor and the other terms, the pipe length that we're talking about, diameter, average velocity squared over 2g. The main difference is that the friction factor is now calculated using some different equation. So the Colebrook equation is going to be the main one, although it's a little bit unwieldy. This is, first of all, implicit in F, so you can't explicitly solve the whole thing for F. You can't isolate F out of this equation. I encourage you to try, but don't spend too much time on it, because I don't think you're going to be able to do it. Once you have given up on that, then come back to the video here and you can solve for what an F is for a given set of Reynolds number and other parameters in here, as long as you substitute in a friction factor guess and then work out what it turns out to be, solve for the F that you get, and then sub that in again to get your next guess, sub it in again, get your next guess, sub it in again, get your next guess. This is an iterative solution method that you can use for the Colebrook equation. Your initial guess doesn't have to be that close for you to converge in on the final correct answer, because of how forgiving the log function is. Another thing that you'll notice in here is that there's this term we didn't have before. Previously, the friction factors were just in terms of Reynolds number with this chart. And now, with the Colebrook equation, the friction factor, yeah, it's implicit, but it depends on Reynolds number still. And this other term, epsilon over d. Epsilon is the mean height of the roughness of the pipe. So epsilon over d, mean height of roughness divided by the diameter, is called the relative roughness of the pipe. For a laminar flow, pipe roughness didn't matter because of the no slip condition. So it's kind of like it's already infinitely rough at the edges. But for turbulent flow, there's enough craziness in the velocity that the pipe friction actually matters. It makes a big difference to how much the walls are going to be influencing the flow in the middle and causing extra drag, specifically because there's so much roughness in the flow. The flow in turbulence is moving laterally, not just down the pipe, but laterally across the cross-section at any instantaneous moment. A little fluid element might be going towards the wall or away from the wall, which allows kind of efficient momentum transfer from the walls towards the center of the pipe. It's why the velocity profile looks so different, and also why the roughness of the walls can help influence the flow in the center to a greater extent in turbulent flow than it matters in laminar flow. The actual amount of roughness that's on the wall depends on the pipe material and on how old the pipe and what's been flowing through it. So here's some equivalent roughness values for new commercial pipes, but you have to be careful not to assume the same number is going to be true for older pipes. So glass or plastic is nominally smooth, which has no roughness, and then depending on what kind of pipe it is, you can have a fair bit different roughness. So concrete, quite rough. Copper or brass tubing is relatively smooth, although not quite as smooth as glass or plastic, and so on. Colebrook equation, again, is implicit, so it can be a pain to solve. Now, instead of that, we have this equation, so the Haaland equation. If you'd like to get a faster answer and don't need the kind of accuracy that the Colebrook equation iteration method can give you, this is great for a first guess. Now, suppose you don't want to do any of that. Suppose you are more of a visual learner and you want to read things very quickly off of a chart. Well, then you are in luck because we have the Moody chart right here. Here's how this works. You have Reynolds number on a log scale across the bottom. We've got the resulting friction factor on a log scale across the left-hand side, and the relative roughness also on, well, not quite a log scale, on the right hand side. Now, why isn't this one a log scale? Because these are actually the labels of these curves. So this curve here, which goes up there, I'll try and do some mouse tracking and over onto this side. This is the curve with a relative roughness of 0.002. So what you do is you say, for whatever pipe you've got, you calculate the roughness, maybe from this table if you're not given what the roughness is, then you divide by the diameter to find the relative roughness. And suppose your relative roughness is 0.0001. That means you are talking about this curve. Now you look up your Reynolds number, and suppose your Reynolds number is 10 million. Okay, so you follow this curve over to where Reynolds number is 10 million, and that intersection is right here. And that tells you, if we go over and read to the left, trying not to lose track across the legend, it looks like we end up right here, which is a Darcy friction factor corresponding to 0.01, 0.02, 0.03, 0.03. Well, no, not quite, because this is actually, these divisions here are counting up smaller amounts. So this is 0.01. This is 0.015, so this must be 0.01, 0.011, 0.012, 0.013, 0.014, 0.015. Yeah, there we go. So this is this one here that we wanted, 0.0112, 0.012, corresponding to 10 million Reynolds number for a relative roughness of 1 E-4. And that's how you use the Moody chart. It's probably not going to be extremely accurate for you either while reading off the chart, but once you get good at it anyway, it can be faster than substituting things in to the Haaland equation, and almost as accurate as this, nominally as accurate as the full Colebrook equation, if your ability to read off the chart is flawless. The best part about the Moody chart, I think, is not really the ability that it gives you to calculate friction factors, but the intuition it gives you about how friction factors work. So you can see that over here in this range, the friction factors are constant with Reynolds number. And in this situation, the head loss depends with constant friction factor on the velocity squared divided by the pipe diameter. Okay, that's fairly simple. It increases linearly with length of the pipe, decreases linearly with diameter of the pipe, and increases with velocity squared. That's only in the situation of extremely rough, turbulent flow. On another extreme, if we're in the laminar flow regime, then because friction factor goes like 64 divided by the Reynolds number, you can see that the friction factors for laminar flows, where they line up with the turbulent ones, ends up being a lot lower, especially at these at these high Reynolds numbers here. So if you can somehow maybe use laboratory smoothness conditions on the walls of the pipe, then you can maintain a lot less head loss for flow in that pipe than you would normally get if it would kick into turbulence like normal. So, all right, so the flow, let's suppose you can do that. If you increase the Reynolds number, then for a given pipe, increasing the Reynolds number means you're increasing the velocity, and you'll find that even though the friction factor is going down, the head loss is going up, because head loss goes like friction factor multiplied by velocity squared. So if friction factor is going like 1 over velocity, then multiplying that by velocity squared, the head loss still increases with velocity, but not to the same extent that it does in fully turbulent flow. So we have friction factor decreases with Reynolds number and increases with relative roughness. Great observation. Generally, for a given roughness of pipe, as you increase the Reynolds number, the friction factor goes down. Friction factor goes down for laminar as well with increasing Reynolds number. This does not mean that the head loss goes down, because remember, that goes like friction factor times velocity squared. Another thing to note from this is that there's a really notable exception, and that's the transition to turbulence. So friction factor decreases with Reynolds number, except if you've increased the Reynolds number to a point where that has actually switched on the turbulence, then your friction factor rises a fair bit. If you can keep the flow laminar, friction factor will be much lower. In the limit of perfectly smooth pipes, the roughness is 0, and then we have the bottom part of this. So that's the lower friction factor that you can get for turbulent flow. In addition to that, it's more likely to delay the onset of turbulence maybe a little bit, make things a bit better for this transition flow region there. And then we can substitute in an epsilon equals 0 to the equation and see how it behaves for perfectly smooth pipes. This allows you to simplify this a bit and rewrite 1 over root f as 2 log 10 of the Reynolds number of root f, which is minus 0.8, which is the Prandtl equation. This is the lower limit for the turbulent friction factor. If you don't know what the roughness is, you know that it's still going to be at least a friction factor calculated through this equation. So it's not going to give you a lower friction factor than this as long as you are still in turbulent flow. In the limit of extremely rough pipes, you can also calculate the upper bound for the friction factor for a given Reynolds number, and that's the von Karman equation. Last piece we need is the kinetic energy correction factor. Again, experimentally, for turbulent flow is 1.05, not the 2 that it was for laminar flow. Final bit of information here is that if you don't want to iterate or use the Moody chart, then you can use these explicit relations, and these have eliminated the friction factor. It's 3 equations which can save a lot of time depending on what it is that you're trying to solve for. So these are kind of neat. Let's see what they have. We've got velocity flow rate. We've got length of the pipe, diameter of the pipe, roughness, and then some kinematic viscosity, diameter, velocity, flow rate. Okay, so this tells us the head loss in terms of velocity, flow rate, roughness, pipe diameter, length of the pipe. So this would be useful if you know the pipe parameters and what kind of flow you're expecting. Note that Reynolds number is not in here either. This would be if you happen to know that the Reynolds number is in a range where this is valid and the roughness is in a range where this is valid, and it's a circular pipe. These are circular pipes only. Then you could calculate the head loss directly from subbing into this equation. Alternatively, for Reynolds number greater than 2000 only, less restrictive than the other equations that we've got here, we've got an equation for what velocity flow rate you would expect if you know what the head loss is. And finally, this is maybe the most time-saving one. This is what pipe diameter you should have or you would need to design if you know what your roughness is going to be, you know, the flow rate that you want to get and the head loss that you can that you want the pipe to have. Very time-saving over doing quite an iterative approach with the Colebrook equation. The reason that pipe diameter is so difficult to solve for with the Colebrook equation is that so many things depend on it. So suppose that you have some system and you say, all right, well, I want to get 1,000 liters a minute from this part of from this place to this place, you're changing elevation. You know maybe what kind of head loss that you want to have, so you would know what pump maybe head loss you can deal with, and you need to know what the diameter of the pipe is. Well, the diameter doesn't just show up right there. The head loss doesn't let you determine what the friction factor is unless you know the Reynolds number, and you can't find out the Reynolds number unless you know the diameter and the velocity. The flow rate doesn't determine the velocity if you don't know the diameter. So diameter is really coupled in this equation in a lot of different ways, and having a shortcut to solve for that directly if you know the flow rate and the head loss that you're looking for a given length of pipe is definitely a real time saver. Now, if you do go design piping systems, I need you to know that Schedule 40 steel pipes, a 1/4 inch steel pipe, is not talking about the outer diameter. 1/4 inch is not talking about the inner diameter either. In fact, it's none of those if it's a Schedule 40 steel pipe. A 1/4 inch has an inner diameter of not 0.25 inches, but 0.364 inches. And an 1/8 inch, instead of 0.125, is 0.269. It's much worse for these smaller sizes than for larger ones. So a 3-inch pipe is almost 3 inches, just a little bigger inner diameter. They're all bigger, but the smaller ones are off by quite a lot. The reason for this is when Briggs standardized the piping sizes 150 years ago or so now, he wasn't trying to make them exact. He was just saying, here's a nominal size. The inner diameter is going to be close to the labeled size. So 1 inch is going to be close to 1 inch inside, 1/2 inch is close to 1/2 inch inside, and so on. And in addition to that, when manufacturers found better materials and made or better processing techniques and were able to make steel pipes have thinner walls and hold just as much pressure, they left the outer diameters the same and ended up increasing the inner diameters further from Briggs's original specification. So we're left with a Schedule 40 steel pipe system where the actual inner diameter is well defined. It's just nothing like the label.